Hello everyone, I'm Ceren Kocaogullar from the University of Cambridge. Today I'll talk about our paper named Putting Private User Discovery in Anonymity Networks. This paper is a collaboration with Daniel Hugenroth, Martin Klebman, and Alistair Beresford. In the recent years, we have achieved widespread adoption of end-to-end encryption for protecting what is said over communication channels. However, the same cannot be said for protecting when, where, and to whom things were said, while again and again we see real-world examples showing how important it can be. We call this type of privacy, which is concerned about protecting the information about a message other than its content, metadata privacy. And we can achieve metadata privacy using anonymity networks such as Loopix. But how do users find each other in networks like this? Well, anonymity networks usually don't provide native lookup mechanisms, so oftentimes the users need to somehow find the other user's public key. Similarly, URLs on Tor look like this, and an address on NIM looks like this. NIM is a commercial deployment of the Loopix anonymity network with more than 700 nodes. On the other hand, we're used to having things like email addresses, phone numbers, and memorable URLs in regular networks. Currently, with anonymity networks, business cards would look like this, but we think people would prefer them to look like this instead. And we think that the lack of a usable user discovery mechanism is an important factor in why things like end-to-end encrypted messaging apps are widely popularized compared to systems that provide metadata privacy. And this is why we designed Pudding. In Pudding, we use email addresses as usernames, which are not only readable, but they're already in contact address books of phones. And therefore, the anonymity network can automatically obtain the keys of the user's friends in the same way that WhatsApp, Signal, and iMessage does. We built Pudding as an application layer on top of the Loopix anonymity network. Loopix architecture looks like this. There are these special kinds of nodes called provider nodes, and they sort of serve as inboxes and outboxes for users. And then there are multiple layers of mixed nodes that relay the messages. When Alice wants to send a message to Bob, she picks one node from each of the relay node layers and creates a header that is encrypted in layers, where each layer can be decrypted by one of the nodes in the message path. So as the message moves through the network, each node knows the node that comes right after it and the one that comes right before it. As long as one of these relay nodes is honest, it is difficult for an adversary to determine who is talking to whom. And this is one of the ways that Loopix achieves metadata privacy. Loopix also supports this useful primitive called single-use reply blocks or SURBs. A SURB is basically a header that the sender of the message, in this case Alice, prepares and attaches to the payload. Bob can then use the SURB as the header of his reply and send a message to Alice without having to know her public key or network address. Now let's look at what happens if we try to use the user discovery model used in regular networks and things like end-to-end encrypted messaging applications on anonymity networks. In this model, there is a key lookup server that provides the users with the public keys that they're searching for. Now let's assume that the discovery server is malicious. The first problem here is that when Alice searches for Bob by his username, the discovery server learns that Alice is looking for Bob and therefore they're likely friends. There is also another problem. The discovery server can give Alice a key that doesn't belong to Bob. Now let's look at the scenario where this time Alice is malicious. What she can do is to search for any possible username and learn if that username belongs to a registered user or not. Well, this is an anonymity network, so Bob might want to hide the fact that he's a user in this network. These simple examples show that private user discovery in anonymity networks is not an easy problem to solve. So we built Putting Private User Discovery Protocol with 4 goals in mind to provide a similar level of security and privacy to the anonymity networks themselves. First of all, we want unlinkability so that the adversary can't figure out who is friends with whom. We also want security against impersonation, where the adversary can't redirect user messages. We want external identity verification so that the user's identities within the system can be verifiably linked to an external identity, like an email address. This way, for example, journalists can sign up to Pudding with their institutional email addresses, and whistleblowers can make sure that they are talking to the correct person. Lastly, we want membership unobservability so that an adversarial user cannot figure out if a username belongs to a registered user or not, unless the owner of that username wants to disclose this information. Pudding is made of 4 subprotocols. Lookup and ContactInit allow users to discover other users and reach out to them. AddFriend allows users to establish long-term connections with each other so that they don't need to use Pudding every time they want to talk to each other. And lastly, we have the register protocol that is optional. This one allows users to become discoverable via username, but the users don't have to register to be able to look up other users. Now let's look at the first 2 subprotocols, Lookup and ContactInit. Now let's look at the Pudding setup. Pudding is an application layer protocol which requires no changes to the Loopix network infrastructure. In Pudding, we have multiple discovery nodes, more specifically 3f+1 discovery nodes, where f is the maximum number of faulty nodes. This way, Pudding continues to operate even if less than a third of the discovery nodes are broken or malicious. Now, before diving into how Pudding works, let's keep the same setup and look at another idea that might help Alice find Bob. What Alice does is she sends requests to the discovery nodes with Bob's username, looking for him. And each of the discovery nodes generates a SURB that will allow Alice to send a message to Bob. And Alice waits for f+1 responses out of 3f+1 discovery nodes to make sure that she has the correct SURB that will bring her message to Bob. And then she can use the SURB as the header to her message and send a message to Bob. So the first thing to highlight here is that Alice has waited for f+1 of the same SURB from discovery nodes to reach out to Bob because she wants to make sure that she's talking to the correct person. But the original SURB generation process is non-deterministic. So we have modified this process to make it deterministic. It works by seeding the pseudorandom generator with a hash of the lookup email address, a nonce, and also a secret value that is shared among the discovery nodes. The second problem with this scheme is that even a single malicious discovery node who collaborates with a malicious provider that Alice uses can recognize the SURB that the discovery node has provided and the SURB that Alice is using, and therefore understand that it was Alice who searched for Bob and break the unlinkability goal. Now let's look at how Pudding works. We're going to be focusing on only one of the discovery nodes for simplicity, but all the operations happen across all discovery nodes. Also, we assume that Bob has already registered to the system with a public key to which he has the corresponding private key. When Alice searches for Bob by his username, each discovery node creates a blinding factor. This blinding factor is derived from the same seed used in the deterministic SURB generation process. Therefore, just as in the SURBs, all discovery nodes generate the same blinding value for a given user lookup request. Then the discovery nodes use this blinding factor to blind Bob's public key. In the next step, the discovery nodes also generate a SURB using the deterministic SURB generation process that we have introduced, and they respond to Alice with this SURB as well as the blinded public key. They also send the blinding factor to Bob. When Alice receives the SURB and the blinded public key, she uses the blinded public key to encrypt a note that she wants to send out to Bob. Then she creates a new message where the payload is this encrypted note as well as the SURB that she has received from the discovery nodes. Note that this is different from what was happening before, where the SURB was directly used as the header for a new message. Instead, what happens here is that Alice sends this message out to the discovery nodes, and the discovery nodes use the SURB in the message that they receive from Alice as a header for a new message. And then they send out the new message, which goes out to Bob. In a sense, discovery nodes serve as reflectors for this message here. When Bob receives this message, he blinds his private key with the blinding factor that he has received from the discovery nodes before. So he can use the blinded private key to decrypt the message that Alice has encrypted with the blinded public key. Now let's look at how we achieve membership unobservability with this scheme. When Alice searches for a username that doesn't belong to a registered user, the discovery nodes blind a fake public key and generate a SURB for a fake address, and they respond to Alice with these values. When Alice receives these values from her perspective, she cannot tell if these are fake or real because these are pseudorandom values. So she still uses them to generate a message like she did before and send it out to the discovery nodes. The discovery nodes then reflect this message, but the message gets dropped along the way because the SURB was not for a valid address. In the end, because SURBs and blinded keys don't reveal whether a user exists or not, and also because Loopix hides the messaging patterns, Alice can't tell if there is no such user that's registered as bob@mail.com or if there is such a user that chose not to respond to Alice. Now let's look at the next subprotocol of pudding, called addFriend, that is used for establishing long-term connections with other users. addFriend protocol is used for Bob and Alice to be able to establish an authenticated communication channel after Alice searches for Bob and reaches out to Bob. This only happens if Bob accepts Alice's contact request and decides to respond to her. One important thing here is that we want to ensure that the users are communicating with the correct users that they were searching for. So Alice should be able to verify if she's talking to the owner of bob@mail.com, and the same also applies for Bob if Alice has also provided her username in the initial message that she sent to Bob. But this is not something that Alice has to do. Again, going back to the whistleblower case, if Bob could be a journalist and Alice could be a whistleblower, and Alice would not need to provide any username to be able to then establish a long-term communication channel with Bob. In addFriend subprotocol, we use a modified Sigma authenticated key exchange protocol. We have adapted the original Sigma protocol to support blinded key signatures. We use Sigma because it's fairly simple and proven correct, but another authenticated key exchange protocol could be substituted in its place. Now let's look at the last subprotocol of pudding, that is register. Registration, as we mentioned before, is optional in pudding. The users don't have to register to be able to discover other users. It's only needed for being discoverable. Registration in pudding is also very practical. There is no need for users to click on multiple links or respond to multiple emails. They just need to reply to a single email. And the discovery nodes can still have high confidence in authenticating the email address. In a sense, registration is also paradoxical because we need external verification of email addresses to achieve membership unobservability. So let's think of the case where we were not doing any sort of username authentication and the users were able to register with pseudonyms. What could happen then is that any user could try to register with any pseudonym, and if they get a positive response from the discovery nodes, they would know that that is an username that does not belong to a registered user, and vice versa. So that's why we need authentication of usernames to achieve membership unobservability. Now let's look at how register subprotocol works. When Alice wants to register with an email address, she sends a message to the discovery nodes including this email address. And she also picks one of the discovery nodes to be in charge of the registration process, and she sends the ID of that node also along with her email address. In this case, this node is D4. Then each of the discovery nodes generate a challenge value and send it out to the chosen node, that is D4. And what D4 does is it collects these challenge values from all discovery nodes, also generates a challenge value itself, and sends Alice an email including these challenges along with her contact information and username. When Alice receives D4's email, she responds to it. And her response should include the original email from D4 in its body. This might look like a lot of work, but it's actually not, because most of the email clients automatically handle this when you hit the reply button. So that's what Alice does here. Alice's response to D4 gets signed on its way out by the mail service provider. This is standard practice, and the signature is called the DKIM signature. It is a digital signature on the header of an email that's used for confirming the origin of an email. The DKIM signature allows the recipients to check that signature against a public key that is published by the domain owner in a DNS text record. This verification confirms the email that the email was sent by an SMTP server that was authorized by the domain owner, and this helps ensure the sender's identity has not been spoofed. When D4 receives Alice's response, it distributes this email to the other discovery servers, and each of the discovery servers checks the validity of the DKIM signature and also checks if its own challenge is included in the email. If both the verifications are passed, then the discovery nodes register Alice with the email address that she has provided. Alice then waits for 2f+1 registration successful messages from discovery nodes. Having 2f+1 as the threshold value here allows our protocol to be resilient even if the set of Byzantine faulty discovery nodes change among different subprotocols. Now let's look back at the goals that we have set for ourselves. We have achieved unlinkability by using a deterministic SURB and blinded key mechanism. We've achieved security against impersonation because users wait for responses from more than 1/3 of the servers. We've achieved external identity verification by using DKIM signatures. And lastly, we have achieved membership unobservability because SURBs and blinded keys don't reveal if a user exists or not. We have implemented pudding on the NIM network with no changes to the infrastructure, and we have found that registration and discovery are quite fast. All operations have mean latencies that are less than 13 seconds, and keep in mind that these are one-time operations. We also found that the performance is quite influenced by the anonymity network's throughput limits, so if you have a faster anonymity network, our protocol also performs better. And that's pudding. You can find our paper and GitHub repo using these QR codes, and you can reach out to us via this email address. Thank you very much for listening.